Today we'll be looking at the ideal gas law. So follow along in your notes and fill this in. Now, we've already looked at in this chapter gas laws, Boyle's, Charles, Gay-Lussac, combined gas law, dealing with variables of P, V, and T. And we looked at situations where two of our total four variables were constant, or as in the case of the combined gas law, only the number of moles were constant. Well, all of those laws look similar to each other because they're really all versions of one greater law, the ideal gas law. And the ideal gas law is really the only gas law that deals with all four variables. And unlike the others, we don't have ones and twos. So there's no initial pressure, initial volume. There's just the pressure. So the actual ideal gas law itself is PV equals nRT. So the equation you're going to be using for today's homework are all based around this equation, PV equals nRT. And really, this is the universal gas law, and it deals with pressure, volume, temperature, and the number of moles. Now, P is pressure, just like you've seen in all the other equations we looked at. When you saw capital P, it was dealing with pressure. And you can have kilopascals, which we typically have, but you can also have pressures of atmospheres, or you can have millimeters of mercury. Really, pressures can come in a number of different units. Most of the time you'll see kilopascals, but atmospheres and millimeters of mercury are other versions of pressures. And when you're using PV equals nRT, you can use any of these three units, but it's really important which you're in, and you'll see why before we're all said and done. So pressure can actually be in any of the units, and you need to recognize which unit of pressure you're actually in because it's going to drive other things about this problem. Now, volume, unlike before where as long as both were in milliliters or both were in liters, in Boyle's law where we had P1 V1 equals P2 V2, we didn't really have to have one particular unit. Now, in the case of the ideal gas law, the volume has to be in units of liters. So if you're given milliliters, remember you need to change that to liters by dividing by 1,000. So if you're ever in milliliters, it can't stay there for the ideal gas law. You've got to convert that into liters. Next would be n number of moles. Now we've talked about the number of moles as one of our variables, but we haven't had an equation yet that used that. But when you see n in PV equals nRT, n stands for the number of moles. And just like volume had to be in units of liters, how many moles we've got, that's a unit. Remember, it's related to mass. So if we're in grams, we have to convert to moles. Just like if we're in milliliters, we have to convert to liters. Remember, if we are given a mass, we have to change that into number of moles. And you've done this probably hundreds of times so far. So if we have X number of grams, remember we don't want grams, we want moles. And this is a molar mass conversion problem. For every 1 mole, we have the mass on the periodic table. So if it was something like grams of water and we wanted moles of water, then it would end up 18.0 down on the bottom here. So remember, if we're given a mass in a problem, just like if we're given milliliters in a problem, you have to convert that to a specific unit. In the case of amount of particles, we can't leave it in mass. We have to change that into the unit of moles. Now, the next one and final variable in our equation is the variable T. And remember, that's temperature. That's got to be in Kelvin, just like it was for all of our other gas laws. We have to be in temperatures of Kelvin. And that's actually the one that you're used to, because in every gas law we've looked at, it was always Kelvin temperature. So we always had to change from degrees Celsius into kelvins. So we've got four variables, P, V, N, and T. And the ideal gas law includes the relationships between all four of those variables. And remember, pressure can be any of the above units. Volume has to be liters. The amount has to be in moles. And the temperature has to be in Kelvin. Those three are very specific units. Now, we've got five things in PV equals nRT. So what's the R? If we only have four variables, then R can't be a variable, which means R has to be a constant. It's called the universal gas constant or ideal gas constant. And unlike the constants we talked about in the math for where did P1 V1 equals P2 V2 really come from and so forth, those were constants that were only constant when the number of moles and the temperature was constant. Change either of those and you get a different constant. That's why we got rid of the constant and dealt with just P's and V's. Well, in the case of the ideal gas law, we don't have anything left. Everything is involved in this situation. So R is actually a universal constant. So no matter what the situation, R is always going to be the same value. Now the thing about R is, even though it's the same value, because we can have different pressure type situations, there's actually different uses or different numbers for R. And really the only difference is you'll notice is what is our pressure unit? If we're dealing with the number 8.31 for R, if you look at the unit, you're going to get liter kilopascals over mole Kelvin for your R value. So notice it's got kilopascals in there. So if you're dealing with a pressure in kilopascals, we use that value for R. If we're not in kilopascals, we either have to change to kilopascals, which is a pain, or use a different value for R. So if we're not in kilopascals, then we don't use 8.31. We're going to use a different value for the ideal constant. And if we're in atmospheres, we would end up using 0.0820. Now, this is another value for R, but it's a value for R with a different pressure unit. And these two actually equal each other. 8.31 liter kilopascals over mole Kelvin does actually equal 0.0820 liter atmospheres over mole Kelvin. If you actually took the kilopascals and converted it to atmospheres by dividing 8.31 by 101.325, which is really what one atmosphere equals in kilopascals, you would get 0.0820. That's where that number comes from. So remember, these are the same thing. They're both values of R. They're just R when you're using different pressure units. So if you're in atmospheres, we've got to use this on the homework assignment. Now, if they're dealing with millimeters of mercury, which remember we talked about is the same thing as the unit of torr. They're identical to each other. So if we've got millimeters of mercury, or technically torr, now we're going to use 62.4. So really we have three different R's that are all the same thing, the constant R. The reason we use the three is to avoid always having to convert our pressure units. Now, the one nice thing about our values for R, unlike some of the other things like Avogadro's number said you have to memorize that. And what does STP stand for? I said you had to memorize those numbers. The values of R will all be given on the test. You just need to know when you're going to use which one. And remember, that's driven by pressure. So whatever your pressure unit is going to determine which R value you should use. So if the problem says find the pressure in kilopascals, you're going to use this one because it said find the pressure in kilopascals. If in the problem they tell you what the pressure is in atmospheres, then you're going to use this one because that's the R value that deals with atmospheres. So remember, P and R are connected to each other. Whatever your pressure is, that's going to drive which R value you need to get. So pressures drive the R value. And remember, these are numbers you don't have to memorize. They'll be given on the test. You just need to know when to use them and when to use which one. And remember, that's going to be driven by your pressure. Now, the ideal gas law I said is actually related to every gas law. All gas laws actually come from the ideal gas law. So that means you can actually derive Boyle's, Charles, Gay-Lussac, and the combined gas law, as well as a whole bunch of gas laws we don't really give formal names to from this one equation. And sometimes when you're on the test, you can't remember, what was Boyle's law? Well, there is actually a way, if you remember PV equals nRT, you can get all of the rest. And it's a useful thing to see at least one time, because if you're not sure what Boyle's law is, what is the relationship between pressure and volume, or what is the relationship between volume and temperature, there's actually a way to see it using PV equals nRT. So PV equals nRT is our ideal gas law. It's got all of our variables in it. All the other gas laws used some variables, and some of our variables were ending up constant to each other. But if you want to see the relationship between pressure and volume, pressure and temperature, volume and temperature, pressure, volume and temperature, and so on, all you really need to do is manipulate PV equals nRT. Now, if you think about it, what's the only constant in PV equals nRT? Well, that's R. So if we solve this equation algebraically for R, we're actually going to see every form of every gas law we've got. So if we want to solve for R, that means we need to get rid of N and T. Well, that means divide both sides by N and T, and I maintain the equality, and my N and T's cancel. So R actually equals PV over NT. Well, Boyle's law, N and T were constant. So what we're left with, if we get rid of N and T because they're constant, we've got P and V. Charles' law was V over T. That meant P and N were constant. Well, if P and N were constant, then they're out of our equation. And V1 over T1 would equal V2 over T2. So really, every single equation comes from the ideal gas law. So if we can't remember what is the relationship between pressure and temperature, well, that means V and N are constant. So P1 over T1 equals P2 over T2. So remember, every single gas law comes from the ideal gas law. It has to. So if you can't remember Boyle's, Charles, Gay-Lussac's, or the combined gas law, because in the combined gas law, N is constant, so all we're left with is P1 V1 over T1 equals P2 V2 over T2. Remembering PV equals nRT and solving it for R, we see every equation we've ever learned. So we've got this universal gas law that we never ever use or never ever talk about. But we've got always P and V on top and N and T on bottom. Since they equal R, then that means any new pressure and volume and number of moles and temperature would have to equal the same thing. Well, if they both equal R, then they both equal each other. And all you really have to do is cancel out anything that is constant. So if P and N are constant, V1 over T1 equals V2 over T2, and so on. So this is really how the ideal gas law gives us a form of every single equation we've ever talked about, plus ones we don't have a name for. If V and T were constant, we don't have a name for it, but if V and T are constant, I can guarantee P1 over N1 has to equal P2 over N2. We could call it Mr. Brown's law if we wanted. So that's how you can use the ideal gas law to derive all of the other equations that we've looked at in the chapter. Now, what's an ideal gas law problem look like? So a typical PV equals nRT problem. What's the volume of 14.2 grams of O2 at STP? Remember, STP is a hidden temperature and a hidden pressure. So they're actually telling us a temperature and a pressure and an amount, the mass right here, and they're asking us for V. That sounds like they're telling us everything but one of our variables in PV equals nRT. So what we're going to be using here is that base equation, but we're solving it for V. Remember how our algebra works. If we want to solve for V, it has to be on top and alone. Well, it's already on top. To get alone, we divide both sides by P. And what we want is nRT over P. That's what we'll use to solve this equation. We just need to get N and R and T and P. Once we've got those four things, we can plug in the equation and we'll know the velocity. So that's the equation that we're actually going to look at here. So V is going to equal nRT over P. Question is, what's N? What's R? What's T? What's P? First off, N. Well, N is the number of moles. And if you look up top, they never tell me how many moles I've got. But remember what I circled, the mass. That is related to the number of moles. So you can set up a quick, easy dimensional analysis problem like you've done hundreds of times dealing with mass and moles. I know it's O2. So for every 1 mole of O2, I've got 32.0 grams. So divide 14.2 by 32.0, and I know how many moles I've got. So 14.3, 32.03 sig figs. That's why I rounded it to 0.444 moles of O2. So now I know N for my equation. So I can plug that into my N place. Now, R and T and P. Well, here's my N, 0.444. So that's taken care of. Notice it gave me a pressure as STP. It didn't really tell me what pressure. Well, I know standard pressure is 101.3 kPa, and I know standard temperature is 0 Celsius, which is 273 K. So that's where this value comes from. Well, if I'm going to plug in 101.3 kPa in the bottom, then that means I'm stuck in kilopascals. And the R value that dealt with kilopascals is 8.31. Now, since I also know standard pressure is 1 atmosphere, could I plug in 1 ATM here on the bottom if I wanted to? Yes. But that, remember, you would need to get the R value that deals with atmospheres, and that would be the 0.0820 value. So I could also use those and get the exact same answer. But I generally remember standard pressure is 101.3 kPa, so I went with the 8.31. Now at this point, you've got everything for solving the problem and correct significant digits. Remember, your calculator is going to spit out a bunch of stuff. All the ones in the top row have 3, one in the bottom row has 4, 3's less, so I'm going to round my final answer to 3, and I get 9.94 liters. So really, just establish what all of your variables are, and based upon what pressure you use, remember that's going to determine what R you use. So this is what a typical ideal gas law problem looks like, and this is what many of the problems on today's homework are going to deal with. You're just solving for a different value in PV equals nRT. So all in, I think, like the first 3 on your worksheet, because the worksheet itself, I guess, is a total of 6 problems. And really the first 3 are all variations of different variables in PV equals nRT. So what we did here is very similar to what you're going to do in the first 3 problems. Well, what are the other 3 problems? Well, they also deal with the ideal gas law. But the ideal gas law, PV equals nRT, is really something that doesn't work in its current form in all situations. Sometimes we may know the density of a gas. Well, density really isn't in PV equals nRT. but there are things related in PV equals nRT that would actually give us a density. So what we're going to look at is a couple of other forms. It starts with PV equals nRT, and we're going to substitute different things into it to derive different equations. So first three problems on your homework are going to be PV equals nRT. The other three problems are going to deal with substituted forms of ideal gas law. So what we're really looking at is other expressions of the ideal gas law. It still equals, or it still is the ideal gas law. It's just going to look slightly different so we can handle other situations. Now, molar mass is going to be a capital M in the equations that we look at here. So let's say we want to deal with an equation that has molar mass in it. Well, remember, molar mass is actually related to the mass and the number of moles. Well, PV equals nRT, N is in PV equals nRT. Well, if molar mass is the mass per mole, which means mass over moles, if we knew the mass and we knew the number of moles, we could divide and we'd have the molar mass. Well, if molar mass equals mass over the number of moles, then that means the number of moles N would equal the mass divided by the molar mass. So I can substitute that into PV equals nRT, and now I get this. PV equals mRT over the molar mass, M representing the mass. So this is a slightly different form of PV equals RT, but this is pretty close to what we had before, and it's not in a final form yet. There's other things we want to do. So this is not an equation you're ever really going to use here. I guess there are some situations where you could use it, but you don't really need to. This is just one substitution to PV equals nRT to slightly modify an equation. But we're going to go a further step with it. So if we solve that equation for molar mass, what we end up with is this. Molar mass equals mRT over over PV. Well, why is this form a little bit more useful? Remember a second ago I just said density equals mass over volume. Well, if density is mass over volume, and right here in this equation I have a mass over a volume, I can substitute in D density for M over V. And now my equation becomes molar mass equals DRT over P. So now I've got an equation that looks a lot different for P equals nRT, but it's really based upon that same equation. But now I've got a form of PV equals nRT that has molar mass in it and density in it. And that's really a form that I wanted to get to. And if they gave me the density of a gas and its temperature and pressure, I can calculate what the molar mass is. So this is a form of PV equals nRT that can be useful on our homework today. So this is one form of PV equals nRT that you're going to be solving for. So if the question asks you, what is the molar mass of a gas, this is the form we would end up using here. So that's one thing we could do in a particular problem. Now, if we want to find the density of a gas, if we just rearrange that equation a little bit, we get density equals MP over RT. Now, both of these are the same equation, so you don't really have to know both of them. You just really need to know one. So density equals MP over RT, I could use to deal with density or molar mass type problems. So this is probably the form of the equation that you should know. So you should know PV equals nRT, and a substituted form of PV equals nRT would be D equals MP over RT. So if they ask me what was the density, I knew what the gas was, then I know its molar mass. So I can just add that up on the periodic table. If I know its pressure, I know its temperature, and I know what the units of pressure I can get the appropriate are, I can calculate the density of any gas. Or if I know the density and I know its temperature and pressure, I can calculate what its molar mass is. So these are a couple of different forms of the ideal gas law. And really, they're two forms of the same thing. So that's why I circled D equals MP over RT. If you know that, you can use that to solve for other problems. So on the worksheet, the first three are just going to be straight PV equals nRT problems. The fourth and fifth are going to be forms of the density equation here. So solving for density of a gas given different situations. And then the last thing I want you to be able to do is really just solve for mass. Remember, if you're solving for mass, you're solving for moles. So in PV equals nRT, solve for N. And once you know the number of moles, if you know what the substance is, you can use molar mass to convert moles into grams. Just like if we know grams, we have to change to moles. Well, if they ask us to find the mass and all we can find is N, the number of moles, solve for N and then just change that into mass using the dimensional analysis that we've used a number of times before. Now, the only other things I want to mention about ideal gas law are concepts. So we've got the equation PV equals nRT, and then we have the substitutive form of the equation, density equals MP over RT. Well, that's all math related stuff. There's also some concepts you need to know for the test over ideal gas law. And then remember that the test will be coming up at the end of this chapter. I believe it's Friday. The ideal gases really assume all these laws we've been looking at. We're assuming that the ideal gas law, or I should let me rephrase this. Everything we've looked at in this chapter, all the equations we're studying, we're assuming that the gas is following kinetic theory. If the gas doesn't follow kinetic theory, then the equations and all the mathematics we've been doing actually don't work out. Well, the good news is most gases adhere to kinetic theory, which most gases follow the ideal gas law under the temperatures and pressures that we deal with. But there are situations where gases stop behaving as kinetic molecular theory says it's supposed to. And the biggest idea is that gases have no attractive forces. Remember, they're moving fast and far apart. Well, speed kills attractive forces, distance kills attractive forces. That means our gases behave by PV equals nRT and all the other gas laws that we've looked at under most temperature and pressure situations, but not all. Under certain temperatures and pressures, we can actually make gases start to stick to each other, start to have attractive forces. And when that happens, PV equals nRT goes out the window. So what situations do we have where we do have attractive forces? Because really, when we're saying it follows ideal gas law, that means it's following kinetic theory, and kinetic theory says no attractive between particles and negligible volume. Well, when is that not going to be true? Well, under most temperatures and pressures, it is true. So most gases behave like ideal gases and not like real gases. Now, in life, ideal is perfection and we never reach it. With gases, the ideal is the regular everyday situation, and the real situation with gases is the rarity. So under most temperatures and pressures, all the math we've been doing in this chapter work perfectly fine. But there are situations where they stop working and the mathematics go out the window. And really, one of the things you should understand in the test, because there's a couple concept questions related to it, is when does the ideal gas law no longer work? And when do gases actually behave more real? Well, one would be low temperature. Remember, speed kills attractive forces, and when we lower the temperature, we slow down the particles. Eventually, if we slow them down enough, they start to attract each other. So the lower the temperature gets, the less ideal gases behave. And our predictions using PV equals nRT and any of our other gas laws would stop being as accurate. So the lower the temperature gets, the less ideal and more real a gas would be. So if I said you have a gas at 20 degrees Celsius and a gas at 40 degrees Celsius, at 40 degrees Celsius, the gas is behaving more ideally. At 20 degrees Celsius, it's behaving less ideally. But honestly, 40 and 20 are both normal temperatures. It's when we get well below 0 degrees Celsius that we end up with gases stop following ideal gas law. But it would be true that 20 is lower temperature, so it would be less ideal. Now, the other thing we can do to affect how well gases attract each other and the fact that you have a negligible volume is mess with pressure. Under high pressure conditions, we're pushing particles much closer together. And remember, distance kills attractive forces too. Well, when we force gas particles to be close enough together, you can no longer ignore the attractive forces that are inherent to those particles, and then it becomes less ideal and more real. So you need to understand under lower temperature and under higher pressure, gases are less ideal. Now, just as a quick recap of some of the math ideas that we looked at that are relevant here. Um, PV equals nRT is the ideal gas law. What variable in there is related to mass? So if they give us a mass, what variable can we actually find? Or if they ask us to find mass, what variable are we actually solving for? Like in the last problem on the homework. Well, that would be n. So remember, what variable is the mass related to? N. So if they ask us to find the mass, we have to find n and then change mass to moles. If they ask us to find the pressure and they give us the mass, we have to get to moles before we can plug it in PV equals nRT. Next thing, what variable determines R? So I said R is linked to one of these four variables. Which one is it? Well, since temperature, volume, and the number of moles have a constant they have to be in, that means R is related to the pressure. Remember, whatever pressure you're given is what R value you get. Whatever pressure they ask you to find would also determine which R value to use. So R is related to P. And what is the general unit of R? Remember, if we solve PV equals nRT for R, we get PV over NT. That would mean whatever our unit of pressure is going to be here. And also on top, we're going to have liters. And then on bottom, we're going to have our N and T units, moles and Kelvin. So whenever you look at R, the units of R are always going to be a pressure times a liter on top and a mole times a Kelvin on the bottom. And remember, when you're setting up math and writing problems, you should be including units because units should cancel to give you the proper unit. If your units don't cancel, your equation is not validly solved for. Next thing, remember the important substituted form of PV equals nRT for some problems is the density form. Density equals molar mass times pressure over RT. So military police stop riots. So that's one way to remember NP over RT. Come up with your own acronym, but you need to remember PV equals nRT. Pervert is always what I thought. It sounds like the word pervert. That's kind of a weird word that sticks in your head. So pervert is PV equals nRT, and PV equals nRT solve for density. Military police stop riots. MP over RT. What is the M in that? The capital M italics. Remember, that's molar mass. So if you know the substance is gaseous H2O, you know your molar mass is going to be 18.0 grams per mole. If you know the substance is CO2, well, add them up. Carbon is 12.0. Each oxygen is 16.0. 32 plus 12 is 44. That means CO2's molar mass would be 44.0 grams per mole. So remember, if you know the substance, you can determine the molar mass. So if they tell you the substance, you know this variable in that equation. So remember, capital M, molar mass. And those are some of the things you should remember about the ideal gas law and its concepts. And it looks like that's it for this set of notes. Good luck on the worksheet.